Good morning, class, and welcome to this lesson on Modern 3, the work function. Today we will be able to describe the graph of the work function associated with the photoelectric effect. So let's review the photoelectric effect real fast, just to make sure we're all on the same page, okay? So, photoelectric effect. We have a nucleus. This is a nucleus. It has an orbiting electron. A ray of light comes in, hits the electron, and if it has enough energy, the electron will then be scattered off, okay? If there is not enough energy, it will go nowhere. It will go nowhere, okay? And this represents one photon, okay? This electron will absorb one photon, and if the photon has enough energy, it'll be ejected. If it does not have enough energy, it won't be ejected. Okay? And the energy is based off Planck's constant and the frequency. So, higher frequencies have more energy, okay? Higher frequencies have more energy. So, and I just want to point out again, this does not depend on the intensity of the rays, okay? It does not depend on intensity, okay? Intensity would be like intensity of light, pretend being under a very intense light. Being under a very intense light would mean you would have a lot of rays, just a lot of rays hitting you at the same time. That's very intense light. But it does not depend on intensity because this electron is only going to absorb one photon. After that photon, it's either going to be ejected or not, but it's not going to keep on absorbing. Okay, so it only depends on the frequency. Only frequency. Okay, so that's that. If we look at this graph over here, this graph represents the photoelectric effect. Okay, this is called a graph of the work function. So, what is the work function? Let's go over this. So let's go back to our model. Photon coming in, hits a nucleus with an electron around it. Okay, I should make that a solid line. Okay, so this incoming photon is going to have a certain amount of energy. Okay, we're going to say HF. Okay, this photon is going to have a certain amount of energy. Okay, if it has enough energy to eject the electron, that energy is called the work function. So there's a certain amount of energy. There's a portion of this. Let me give you a little bar graph right here, okay? This is the total energy. This is the total energy, okay? A certain amount of this energy, we'll call it the bottom half here, is going to go into just removing the electron, okay? So this is the electron removal. This is the amount of energy on the bottom, if I was making a bar graph, okay? So we're going to call that the amount of energy to remove electrons called the work function, okay? This is the work function, okay? The amount of energy necessary to remove the electron. Okay, simple enough. So what if the total here is more than the work function? What if there's some extra energy? Well, that just means this electron is going to be ejected faster. It's going to have some speed to it afterwards. So basically, this electron is going to be ejected, and the rest is going to be turned into kinetic energy. The max kinetic energy that is going to the electron is going to have. Okay, so looking at this graph right here, we have, notice it starts off at this point right here. So whatever frequency is required, there's a certain frequency, right? A certain frequency means a certain energy. That is the work function. So this right here, this dot right here represents the frequency at which the electron will be ejected. Nothing below it, okay? Nothing. Actually, I shouldn't write that. Nothing below that frequency will work because there's not enough energy. So at this frequency right here, the electron will be ejected and there will be 0 joules of kinetic energy left over. There will be 0 joules of kinetic energy left over. Okay, so at this point right here, it'll be ejected, but then it won't have any movement to it because there is just enough to get it out. Okay, so that means the kinetic energy would be zero at this point right here. And then as frequency increases, the amount of energy increases. So that means there's going to be some left over to give it a kinetic energy. So this is the graph of the work function. Okay, the higher the frequency, the more energy it'll have. Therefore, it'll overcome the work function, and then it will increase steadily. The kinetic energy will increase steadily as we increase here because we have more leftover energy. We have more leftover energy for kinetic. Okay. Now, there's one little tip I want to give you. It's a very common question to say to say based on the graph, what is the work function? What is the work function? Or what this question is really saying is how much energy does it take to eject an electron? Okay, the work function is energy required to eject an electron. So based on this graph, what is the energy required to eject an electron? And I just want to point out that very commonly, if 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 the amount of energy equals the amount of kinetic energy plus the work function, notice the kinetic energy is the y-axis here. We can rearrange this equation. This could be Ke equals hf minus theta. Notice this equation, this is the y-axis. This takes on a very y equals mx plus b format. And so if you were trying to solve for b, which is the work function in this case, what is the work function? And the work function is going to be the y-intercept, okay, which I'm sure you know from algebra. So if you were given a graph like this, and there are numbers on the graph, obviously, what you would just have to do is extend the graph down and find out where the y-intercept would be. And that's probably going to be an approximate thing, but that's a very common question to ask based off this graph, and people get so caught up in looking at this part right here. But that's frequency. Remember, this is the x-axis. This is frequency. That's not energy. That's not the work function. So you can find the work function very easily by just by doing a basic algebra skill of what a straight line is on a graph.